For centuries, telescopes have been our windows to the universe, revealing distant galaxies, alien worlds, and cosmic mysteries hidden in the darkness. But what if everything we know about these instruments is about to change? Picture this: a telescope so radically different, it doesn't just improve on existing designs, it completely reinvents them. The next generation of space telescopes won't just be bigger or sharper, they'll defy every convention, breaking the mold in ways that sound almost like science fiction. And the most exciting part, these revolutionary machines are already taking shape in labs and workshops around the world, poised to transform how we see the cosmos forever. Think about the iconic Hubble or the stunning James Webb Space Telescope, marvels of engineering that expanded our understanding of the universe. Yet even these giants will seem quaint compared to what's coming. We're talking about telescopes with mirrors that unfold like origami, optics guided by artificial intelligence, and materials so advanced they can see wavelengths of light we've never captured before. These aren't incremental upgrades, they're leaps into uncharted territory, driven by breakthroughs in physics, computing, and material science. The next space telescope won't just look different, it'll think differently, adapt in real time, and unlock secrets of the cosmos we didn't even know were there. So why does this matter to you? Because these telescopes aren't just tools for scientists, they're gateways to discoveries that will rewrite textbooks and redefine humanity's place in the universe. Imagine peering into the atmospheres of distant exoplanets with such precision we could detect signs of life, or witnessing the birth of stars in galaxies so far away their light has traveled billions of years to reach us. This isn't just about better pictures, it's about answering questions that have haunted us for generations. And in this video, we're going to explore exactly how these futuristic telescopes will work, why they look nothing like their predecessors, and what they might reveal about the cosmos and ourselves. Strap in, because the future of space observation is stranger and more thrilling than you've ever imagined. When Hubble first opened its eye to the cosmos in 1990, it shattered every expectation. For the first time, we saw distant galaxies with crystal clarity, watched stars being born in stellar nurseries, and even pinned down the age of the universe itself. But Hubble had limits. Its mirror, though groundbreaking, was rigid and unforgiving. Then came James Webb, unfolding like a golden flower in the darkness, capturing infrared light from the universe's earliest epochs. Webb's segmented beryllium mirror and sunshield the size of a tennis court pushed boundaries further, yet even this engineering marvel follows a familiar blueprint, a single, heavy structure launched into space fully formed. Here's the problem: space doesn't play by our rules. Traditional telescopes are like grand pianos, intricate, heavy, and nearly impossible to tune once they're in orbit. A micrometeoroid strike on Webb's mirror in 2022 reminded us how vulnerable these delicate giants can be, and that's where the next revolution begins. Instead of building monolithic mirrors, engineers are rethinking the very shape of observation. Imagine a swarm of small, synchronized mirrors floating in formation, adjusting in real time like a school of fish. Or lenses made of metamaterials so thin they could unfurl like a picnic blanket, bending light in ways glass never could. The constraints of rocket payloads are driving this transformation. Why launch one colossal mirror when you could send up dozens of lightweight segments that self-assemble? Why rely on rigid materials when shape-shifting polymers could correct distortions caused by temperature swings? These aren't just tweaks, they're fundamental shifts in design philosophy. While Hubble and Webb were masterpieces of precision engineering, their successors will be more like living systems, adapting to their environment rather than resisting it. The next telescope won't just capture light, it'll dance with it. For decades, the heart of every powerful telescope has been its mirror, a massive, precisely polished disk of glass or metal painstakingly shaped to capture distant starlight. But this centuries-old design is hitting a wall. Think about it. Launching a single giant mirror into space is like trying to ship a grand piano strapped to a rocket. The heavier the mirror, the more fuel you burn, and the more you sacrifice in payload capacity. Hubble's mirror weighed in at over 800 kilograms, while James Webb's gold-coated beryllium segments added up to a staggering 620 kilograms, just for the optics alone. That's before you even account for the spacecraft, instruments, or that tennis court-sized sunshield. Now, engineers are flipping the script. Instead of fighting gravity with brute force engineering, they're embracing flexibility and intelligence. Picture a mirror that isn't solid at all, but a dynamic swarm of tiny, drone-like segments floating in perfect formation. Each piece could adjust its position in real time, compensating for micrometeoroid strikes or thermal warping without human intervention. Some prototypes even experiment with liquid mirrors, spinning pools of reflective fluid in microgravity that naturally curve into the perfect shape, like a self-healing cosmic puddle. The secret sauce: materials science. Researchers are developing ultra-thin films made of nanomaterials so lightweight they could coat a balloon and still deliver Hubble-level clarity. Imagine mirrors that roll up like posters for launch, then unfurl flawlessly in orbit, or adaptive optics systems powered by artificial intelligence, tweaking a mirror's shape 1,000 times per second to cancel out atmospheric blur, even when there's no atmosphere. These aren't just incremental upgrades, they're redefining what a telescope can be. But the real game changer lies in what these innovations unlock. A traditional mirror can only focus on one type of light, usually visible or infrared. Next-gen designs could morph on demand, switching between wavelengths like a chameleon shifts colors. Want to study ultraviolet radiation from a newborn star? Adjust the surface. Need to peer through cosmic dust in infrared? Tweak the segments. This adaptability could let a single telescope do the work of a dozen specialized observatories, catching phenomena we've always missed because we were looking through the wrong lens. The implications stretch beyond engineering. Every kilogram saved on mirror weight means more room for instruments, longer mission lifespans, or even the ability to launch multiple telescopes for the price of one. Suddenly, studying the universe becomes less about battling physics and more about collaborating with it, harnessing the quirks of space itself to see farther, clearer, and in ways we've never dared to dream. The age of monolithic mirrors is ending, and what comes next will make today's telescopes look like quaint relics of a bygone era. What if the most powerful telescope in history could fit inside a suitcase? That's the promise of foldable space optics designed so compact at launch, they'd make even James Webb's intricate unfolding routine look simple. The key lies in borrowing inspiration from nature and ancient art. Picture a honeycomb, hexagons packed tightly together, efficient and strong. Now imagine that geometry scaled up to space telescope mirrors, with segments that fold flat during launch, then pop into perfect alignment once they reach orbit. This isn't just about saving space, it's about reimagining how we build for the cosmos. Take inflatable mirrors, for example. Instead of hauling heavy glass or metal into space, engineers are experimenting with ultra-thin polymer films that can be rolled up like a sleeping bag. Once deployed, these films are filled with gas or cured by sunlight, forming a smooth, parabolic surface, no bulky supports required. Early prototypes have achieved surfaces precise to within a fraction of a human hair's width, proving that lightweight doesn't mean low quality. And because these mirrors are so light, they could be paired with smaller, cheaper rockets, slashing launch costs by millions. But the real magic happens with modular designs. Imagine a telescope built like Lego blocks, dozens of small, identical mirror segments that self-assemble in zero gravity. If one segment fails, the rest recalibrate to fill the gap, making the system nearly indestructible. Some concepts even use magnetic levitation to position segments with nanometer precision, floating them into place like pieces of a cosmic jigsaw puzzle. This approach isn't just resilient, it's scalable. Want a larger telescope? Just add more modules. The genius of these deployable structures isn't just their engineering, it's their philosophy. Traditional telescopes are frozen in time the moment they leave Earth, limited by the technology of their launch date. But foldable designs open the door to upgrades. Picture a future where astronauts or even autonomous drones could swap out aging components for newer, better ones, extending a telescope's lifespan indefinitely. Suddenly, space observatories could evolve alongside our curiosity, growing more powerful as our questions grow deeper. From origami-inspired sun shields to mirrors that blossom like flowers in the void, these innovations are turning science fiction into blueprints. And when the next generation of telescopes finally takes shape in orbit, their greatest achievement won't be the images they capture, but the way they redefine what's possible when we stop building for Earth's constraints and start designing for the universe's possibilities. The telescopes of tomorrow won't just passively collect light, they'll think for themselves. Imagine an observatory that doesn't wait for commands from Earth, but decides in real time where to point its gaze, like a cosmic detective following the most promising clues. This leap forward hinges on artificial intelligence, transforming telescopes from tools into collaborators. While past missions relied on painstakingly pre-programmed schedules, next-generation systems will use machine learning to adapt on the fly. A passing comet, an unexpected supernova, an AI could instantly redirect its focus, capturing rare events humans might miss during the hours it takes signals to travel between Earth and deep space. What makes this possible is the marriage of two revolutions, unprecedented computing power and vast amounts of training data. Modern AI models have devoured decades of astronomical observations, learning to recognize patterns no single scientist could memorize. They can spot gravitational lensing distortions hinting at dark matter, or subtle wobbles in starlight betraying hidden exoplanets, all while correcting for instrument errors autonomously. Take mirror alignment, where James Webb needed weeks of meticulous adjustments. An AI-driven telescope could perfect its focus in minutes, continuously tweaking individual segments to counteract temperature shifts or micrometeoroid impacts. But the real magic happens in target selection. Picture a telescope orbiting Mars, its AI sifting through petabytes of incoming data to flag the most intriguing anomalies. Instead of wasting precious observation time on empty patches of sky, it prioritizes promising targets, maybe a flickering quasar that could reveal secrets of black hole growth, or an exoplanet with atmospheric chemicals suggestive of life. Some prototypes even experiment with swarm intelligence, fleets of small telescopes coordinating like a hive mind, pooling their data to create a living map of the cosmos that updates itself second by second. This autonomy unlocks another game-changing advantage: speed. Traditional astronomy moves at a human pace, with discoveries often delayed by months of data processing. AI telescopes could analyze light as it arrives, spotting transient phenomena like fast radio bursts or merging neutron stars fast enough to alert other observatories worldwide in time for follow-up observations. It's like giving the scientific community a real-time cosmic early warning system. Yet the most profound shift might be in how we define discovery. Future telescopes won't just answer our questions, they'll propose new ones. An AI trained on known exoplanets might detect bizarre atmospheric patterns that defy existing models, hinting at entirely new planetary chemistries. Another could correlate faint signals across galaxies, uncovering hidden laws of physics. This isn't just automation, it's partnership, where human intuition and machine precision combine to explore frontiers neither could reach alone. The universe has always been full of surprises. Soon, we'll have tools smart enough to notice them all. James Webb's infrared eyes have revolutionized how we see the cosmos, peering through dust clouds to witness stellar nurseries and capturing heat signatures from the universe's infancy. But infrared is just one chapter in light's grand story. The next generation of telescopes will read the universe in wavelengths we've barely tapped, from high-energy terahertz waves to elusive ultraviolet signals. Each slice of the spectrum is like a different language, revealing secrets others can't translate. And with breakthroughs in detector technology, we're finally building instruments sensitive enough to listen. Take terahertz radiation, the long-overlooked gap between microwaves and infrared. This faint whisper of light slips through cosmic dust like a ghost, carrying clues about the birth of molecules, the very building blocks of life. Future telescopes tuned to these frequencies could map organic compounds swirling around young stars, showing us how the ingredients for planets and perhaps life assemble in the void. Then there's ultraviolet, the high-energy glow of hot, young stars and violent galactic collisions. While Hubble glimpsed fragments of this realm, next-gen UV telescopes could track the life cycle of stellar giants, watching as they sculpt galaxies with their explosive deaths. But the real frontier lies in combining these bands. Imagine a telescope that simultaneously observes a star in ultraviolet, visible, and terahertz light, like a musician harmonizing multiple instruments. UV reveals its searing surface, visible light shows its color and composition, and terahertz uncovers the cool molecular clouds it's seeding. Together, they'd tell a complete story, one no single wavelength could narrate alone. This multispectral approach isn't just additive, it's transformative. A galaxy that looks quiet in infrared might blaze with activity in terahertz, exposing hidden black holes or dark matter interactions. The challenge: building detectors sensitive enough to catch these elusive signals. Traditional sensors often drown in noise when pushed beyond familiar wavelengths. That's where quantum-inspired tech enters. Superconducting nanowires, chilled to near absolute zero, can detect single photons of terahertz light. Metamaterials engineered at the atomic scale bend ultraviolet rays with precision impossible for ordinary glass. These aren't just incremental improvements, they're leaps into realms once considered impractical, and the payoff could redefine astrobiology. On distant exoplanets, certain molecules absorb very specific wavelengths. A telescope spanning terahertz to UV might spot the combined chemical fingerprints of oxygen, methane, and industrial pollutants, a trio some scientists call the technosignature of advanced civilizations. Or it could catch the ultraviolet glow of exotic life forms whose biochemistry runs on alien rules. The universe has been broadcasting on all frequencies for billions of years. Soon, we'll finally have the tools to hear it all. Right now, the sharpest images from space come from telescopes with mirrors as big as school buses. But what if we could achieve that same clarity without the colossal hardware? Enter interferometry, a technique that turns multiple small telescopes into one virtual giant. Instead of building a single massive mirror, scientists are exploring networks of modest-sized scopes flying in precise formation. their data combined to mimic the resolution of a mirror as wide as the distance between them. Picture this: two telescopes spaced a kilometer apart could theoretically see details as fine as a single telescope with a kilometer-wide mirror, something utterly impossible to launch as one piece. This isn't just theory. On Earth, projects like the Very Large Telescope Array in Chile already use interferometry to stitch together observations from 4 separate telescopes, creating images sharper than any single dish could produce. But in space, freed from atmospheric distortion and distance limits, the potential skyrockets. Imagine a constellation of suitcase-sized telescopes orbiting in perfect sync, their positions maintained within millimeters. Together, they could resolve features on distant exoplanets, not just blurry dots but continents, weather patterns, even signs of vegetation, or peer into the violent accretion disks around black holes, mapping magnetic fields and plasma jets with precision that would make today's best observations look like cave paintings. The secret lies in timing. For interferometry to work, light waves captured by each telescope must be combined with atomic clock precision. A discrepancy as tiny as a billionth of a second can smear the final image. That's why space-based versions will rely on laser metrology systems, beams constantly measuring the exact separation between scopes, and onboard AI to adjust positions in real time. Some designs even propose using the telescopes themselves as signal relays, forming a self-correcting web where each node calibrates its neighbors. The payoff: unmatched versatility. A traditional telescope is stuck with the resolution its mirror size dictates, but an interferometric array can reconfigure on demand. Need to study a nearby star's planets? Tighten the formation for wider angle views. Want to zoom in on a galaxy's core? Spread the telescopes farther apart, effectively growing your mirror overnight. This adaptability could let one mission tackle questions ranging from asteroid compositions to the structure of spacetime itself. Of course, the challenges are as vast as the rewards. Aligning multiple telescopes across thousands of kilometers in the frictionless void of space demands propulsion systems finer than anything yet built. Then there's the data problem. Combining signals from scattered scopes requires processing power that would dwarf today's supercomputers. But here's the twist: these hurdles are fueling breakthroughs in adjacent fields. The same nanothrusters being developed for interferometry could revolutionize satellite navigation, while the AI algorithms designed to manage telescopic swarms might one day coordinate autonomous cities on Earth. The beauty of this approach is how it mirrors nature's own solutions. Just as ants achieve complex tasks through collective effort, or neurons form intelligence through connection, these distributed telescopes tap into the power of collaboration. They prove that sometimes seeing further doesn't mean building bigger, it means thinking differently. And when the first interferometric array finally opens its eyes, it won't just show us new corners of the cosmos. It'll redefine what it means to explore. Gone are the days when telescopes relied on bulky glass mirrors and rigid metal frames. The next leap in cosmic observation is being built from materials that sound like they belong in a superhero's toolkit: graphene, sheets stronger than steel yet thinner than paper. Metamaterials that bend light in ways nature never intended, and alloys so lightweight they could float on a breeze. These aren't just incremental upgrades, they're rewriting the rules of what a telescope can be. Take graphene, for instance. This single layer of carbon atoms arranged in a honeycomb lattice is 200 times stronger than steel, conducts electricity better than copper, and is nearly transparent. For telescopes, that means mirrors could be made razor-thin yet virtually unbreakable, reducing launch weight by orders of magnitude. Imagine a mirror that's not just light, but also self-healing engineers are already testing graphene coatings that can repair microscopic cracks caused by space debris, using built-in sensors to detect damage and trigger chemical reactions to fill the gaps. Then there are metamaterials engineered to manipulate light in ways no natural substance can. Ordinary lenses rely on the curvature of glass to focus light, but metamaterials can bend photons using intricate nanopatterns etched into their surface. The result, lenses that are flat as a pancake yet outperform traditional optics, free from the distortions that plague thick glass. Some designs even promise perfect focus, capturing light across multiple wavelengths simultaneously, no more trade-offs between ultraviolet clarity and infrared sensitivity. But the real game-changer might be shape-shifting alloys. Materials like nickel-titanium can remember their original form, flexing back into perfect alignment after temperature swings or impacts. For a telescope in orbit, that means mirrors could automatically correct warping caused by solar heat or micrometeoroid strikes, maintaining razor-sharp focus without ground control. Pair this with ultra-lightweight ceramic foams, materials strong enough to support massive structures but light enough to float in water, and suddenly, the dream of football field-sized telescopes in space becomes plausible. The magic lies in how these materials work together. A telescope's skeleton could be 3D printed from lattice-like alloys, combining strength with minimal weight. Its mirrors might layer graphene for durability atop metamaterials for precision optics, while self-healing polymers protect the whole system from space's harsh environment. Even the sunshield, a critical component for infrared telescopes, could evolve into a featherweight membrane embedded with temperature-regulating nanomaterials, unfurling silently in the void. What makes this revolution so exciting isn't just the performance boost, it's the doors it opens. With materials this advanced, telescopes could operate in places we've never dared, orbiting scorching close to the sun for unprecedented views of solar flares, or drifting into the frigid outer solar system to study icy worlds without fear of brittle fractures. They could fold into compact shapes for rideshare launches, then expand like cosmic origami, making space science more accessible than ever. The next generation of telescopes won't just be built, they'll be grown, printed, and engineered at the atomic level. And as these labs on a rocket take their first look into the cosmos, they'll reveal not just the secrets of distant stars, but the limitless potential of human ingenuity when we stop accepting the limits of traditional materials and start inventing new ones. Picture a telescope that doesn't need thrusters or fuel tanks, just a whisper-thin sail, wider than a football field, riding sunlight like a surfer catching waves. This isn't fantasy, it's the cutting edge of space exploration. Solar sails, once relegated to sci-fi, are now proving their worth as real-world propulsion for next-gen observatories. Unlike traditional telescopes that guzzle precious fuel for every orbital adjustment, these revolutionary designs harness the gentle but relentless push of photons streaming from the sun. A single square kilometer of ultra-lightweight reflective material could capture enough solar pressure to maneuver indefinitely, turning what was once a limitation, the faint pressure of light itself, into a free, endless fuel source. The genius of solar sails lies in their simplicity. No explosive chemical reactions, no complex engines, just pure physics. When photons bounce off the sail's mirrored surface, they transfer tiny amounts of momentum, nudging the telescope forward. The acceleration is minuscule at first, like a feather drifting in a breeze, but in the frictionless void of space, where there's no air resistance to slow things down, that gentle push adds up. Over weeks or months, a solar-sailed telescope could reach astonishing speeds, gliding to distant orbits or even escaping the solar system entirely without a single drop of fuel. Japan's Ikaro's mission proved this in 2010, becoming the first spacecraft to demonstrate solar sail propulsion in deep space, cruising past Venus on nothing but sunlight. But the real breakthrough comes when you pair solar sails with gravitational assists, the cosmic slingshot technique that lets spacecraft steal momentum from planets. Imagine a telescope using its sail to reach Jupiter, then swinging around the gas giant to gain speed before unfurling again to ride sunlight toward Saturn. These gravity-powered dance moves could let observatories tour the outer solar system indefinitely, hopping from one orbital perch to another like a celestial nomad. Freed from fuel constraints, such a telescope could monitor decades-long weather patterns on Neptune or track interstellar visitors like Oumuamua without ever worrying about running dry. The implications are staggering. Traditional telescopes like Hubble rely on gyroscopes and thrusters to stay pointed, burning through fuel that eventually dooms the mission. Even the mighty James Webb, for all its innovation, carries a finite supply of propellant, but a solar-sailed observatory, its lifespan could stretch for centuries, limited only by the durability of its materials. Engineers are already testing sails made of aluminized polyamide thinner than a human hair, reinforced with carbon nanotubes to resist micrometeoroid punctures. Some prototypes even incorporate smart materials that can adjust reflectivity on demand, turning different sections of the sail into cosmic brakes or accelerators by tilting toward or away from sunlight. And here's the kicker: solar sails aren't just about endurance, they unlock entirely new kinds of science. A fuel-free telescope could park itself in gravitational sweet spots unreachable by conventional craft, like the unstable Lagrange points where gravitational forces balance in delicate equilibrium. From these vantage points, it could study the solar system's most elusive phenomena, the faint gravitational whispers of passing dark matter, or the slow-motion collisions of dust clouds forming new planets. Some concepts even propose fleets of sail-powered probes fanning out across the galaxy, each carrying a tiny telescope to create a decentralized observatory spanning light years. This isn't just about saving money or extending missions. It's about redefining how we interact with space itself. For centuries, exploration meant fighting against the cosmos, overcoming gravity with brute force, outracing time with fleeting missions. Solar sails flip that script, inviting us to work with the universe's natural forces instead of conquering them. The next great telescope might not roar into space atop a pillar of flame, but silently unfurl like a dandelion seed, catching starlight to wander the heavens forever. And when it finally beams back its first images, they won't just show us new worlds, they'll reveal a future where the cosmos isn't a frontier to be crossed, but a current to be ridden. Imagine a telescope that doesn't just capture light, but manipulates the very fabric of quantum physics to see the impossible. This isn't hypothetical. It's the frontier of quantum optics, where entangled photons promise to smash through barriers that have constrained astronomy for centuries. Traditional telescopes, no matter how large, hit a hard wall called the diffraction limit, a fundamental law of physics that dictates how finely any instrument can resolve distant objects. But quantum entanglement, that eerie phenomenon Einstein called spooky action at a distance, might offer a cosmic loophole. Here's how it breaks convention. When two photons become entangled, they share a quantum connection, instantly mirroring each other's states no matter how far apart they are. Future telescopes could exploit this by sending one entangled photon toward a target, say, a distant exoplanet, while keeping its twins safely aboard the observatory. By analyzing the returning photon alongside its untouched partner, scientists could extract information with unprecedented precision, effectively sidestepping the diffraction limit. It's like having a cosmic microscope that doesn't just magnify distant objects but reconstructs them at resolutions once thought unattainable. The implications are staggering. Current telescopes trying to image exoplanets face a cruel irony. The closer a world orbits to its star, the harder it is to separate their light. But quantum-enhanced optics could distinguish a planet's faint glow from its star's glare with atomic-scale precision, revealing surface features like mountain ranges or oceans. Or consider black holes. Today's best images of their event horizons are fuzzy halos. A quantum telescope might capture the intricate swirls of plasma in their accretion disks, testing Einstein's theories with data sharper than ever. What makes this approach so radical is its departure from brute force solutions. For decades, sharper images meant bigger mirrors like the 30-meter behemoths planned for Earth's mountaintops. Quantum optics flips that paradigm, achieving similar gains not with sheer size but with smarter light. Early lab experiments have already demonstrated quantum superresolution, where entangled photons discern details 20% finer than classical physics allows. Scale that to space, and suddenly a modest 1-meter quantum mirror could outperform a conventional 10-meter one. Yet the challenges are as profound as the potential. Maintaining quantum entanglement over astronomical distances means battling decoherence, the tendency of quantum states to unravel when exposed to heat, vibration, or even cosmic radiation. Solutions might involve cryogenic cooling, ultra-stable laser links, or even quantum error correction borrowed from quantum computing. And then there's the data problem. Extracting usable images from quantum measurements requires algorithms that don't yet exist, blending machine learning with quantum mechanics in ways that push both fields forward. But here's the twist: the hurdles themselves are sparking innovation. The same quantum sensors being refined for telescopes could revolutionize everything from medical imaging to underground mapping. And the pursuit of space-qualified entanglement is accelerating Earth-bound quantum networks, where secure communication relies on similar physics. The telescope of tomorrow might not just reveal new corners of the universe, it could anchor a quantum revolution that transforms technology here at home. This isn't just about sharper pictures, it's about rewriting the rules of observation itself. For centuries, astronomy has been a game of collecting photons and interpreting their stories. Quantum optics turns the telescope into an active participant in that story, coaxing secrets from light that classical instruments couldn't even detect. When the first quantum-augmented observatory opens its eyes, it won't just see farther, it'll see differently, revealing a universe more intricate, more subtle, and more astonishing than we've ever imagined. For all of human history, the question of whether we're alone in the universe has lingered in our collective imagination, written in ancient star charts, whispered in philosophy debates, and etched into every science fiction story. But within our lifetime, that question might finally get an answer, thanks to telescopes designed not just to see planets, but to sniff out the chemical fingerprints of life itself. The key lies in starlight filtered through alien atmospheres, where every molecule leaves a telltale mark on the spectrum of light passing through. Think of it like cosmic forensics. When a distant planet transits its star, sunlight pierces its atmosphere, and certain wavelengths get absorbed by gases present in that alien sky. Oxygen leaves one pattern, methane another, while industrial pollutants like chlorofluorocarbons would scream technology across the light years. Next-gen telescopes won't just detect these gases, they'll measure their ratios, stability, and interactions to distinguish between biological processes and geological false alarms. A whiff of oxygen alone doesn't guarantee life. Volcanoes can produce it, but find oxygen alongside methane, which normally destroys each other unless constantly replenished. and suddenly you've got a compelling case for something breathing, growing, or photosynthesizing on that distant world. The game changer is high-contrast imaging combined with spectroscopy so precise it could spot seasonal changes in vegetation or the glow of city lights. Imagine an instrument powerful enough to separate the light of an Earth-sized planet from its star, a feat like discerning a firefly hovering next to a lighthouse from thousands of miles away. Some designs achieve this with starshades, giant flower-shaped disks flying tens of thousands of kilometers in front of telescopes, casting an artificial shadow to blot out stellar glare. Others use self-adjusting mirrors that cancel starlight wave by wave, revealing planets hidden in the glare. But the real magic happens in the data. Machine learning algorithms will sift through atmospheric spectra, flagging combinations of gases that defy natural chemical equilibrium. Anomalies like red edge vegetation signatures the distinctive way chlorophyll reflects infrared light, or industrial smog could emerge from the noise. And here's where it gets thrilling. We might find life that doesn't follow Earth's rules. Alien biology could produce bizarre gas mixtures, perhaps sulfur-based metabolisms creating thick carbonyl sulfide atmospheres, or organisms harnessing exotic energy sources leaving traces of phosphine in their wake. The universe's chemistry lab is vast, and life might have cooked up recipes we've never even considered. This isn't just about spotting habitable worlds, it's about catching them in the act of harboring something alive. A telescope tuned just right could watch as exoplanet atmospheres pulse with seasonal changes, suggesting continents of alien flora breathing in sync with their star. Or detect the flicker of artificial lights on the night side of tidally locked planets, where civilizations might cluster in eternal twilight zones. Some scientists even speculate about detecting technosignatures, the waste heat of megastructures, or the radio whispers of communication networks leaking into space. Of course, the search comes with profound philosophical weight. A single definitive biosignature would rewrite humanity's place in the cosmos, proving that life isn't a fluke but a natural outcome of universal laws. It could unite us as a species or shake our cultural foundations. Either way, the discovery would echo through every religion, philosophy, and textbook. And that's why these telescopes aren't just scientific tools. They're bridges to answers we've sought since we first looked up at the stars and wondered if anyone was looking back. The next great observatory might not just find new worlds, it could find our cosmic neighbors. Dark matter and dark energy, two phrases that sound like science fiction, yet together make up 95% of everything in the universe. And here's the wildest part, we've never actually seen them. Current telescopes have only given us shadows and hints, like detectives piecing together a crime scene from faint fingerprints. But the next wave of observatories, they're coming armed with tools so precise, they might finally pull these cosmic ghosts into the light. Take gravitational lensing, nature's own magnifying glass. When dark matter's gravity bends light from distant galaxies, it creates subtle distortions, stretching and warping their shapes like reflections in a funhouse mirror. Today's telescopes can spot these twists, but next-gen instruments will map them in ultra-high definition across billions of galaxies. Imagine a survey so vast, it reveals the universe's dark matter skeleton in 3D, showing how this invisible scaffold guides the growth of galaxies over cosmic time. Some projects, like the Vera Rubin Observatory's Legacy Survey of Space and Time, will capture this dance in unprecedented detail, snapping over 800 images of every patch of southern sky across a decade. That's not just a snapshot, it's a time-lapse of dark matter's hidden hand at work. Then there's the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature fluctuations in this ancient light hold clues to dark energy, the mysterious force accelerating the universe's expansion. Future telescopes like the European Space Agency's Euclid or NAS and Nancy Grace Roman Space Telescope will measure these patterns with razor-sharp precision, hunting for shifts that might reveal whether dark energy changes over time or follows Einstein's cosmological constant. The stakes couldn't be higher. If dark energy isn't constant, our entire understanding of gravity might need a rewrite, but the real breakthroughs could come from combining these approaches. Picture gravitational lensing surveys cross-referenced with gamma-ray observations, pinpointing where dark matter might annihilate itself in bursts of high-energy light. Or quantum sensors buried deep underground, waiting for the faintest tremor of a hypothetical dark matter particle colliding with ordinary matter. Some experiments are even repurposing atomic clocks, normally used for precise timekeeping, as dark energy detectors, since changes in the universe's expansion could theoretically alter the flow of time itself at microscopic scales. What makes this search so electrifying is how deeply it cuts to the core of physics. Dark matter and dark energy aren't just missing puzzle pieces, they're evidence that our current theories are incomplete. Every anomaly, every unexplained gravitational tug, is a whisper from the universe that there's more to the story. And when the next generation of telescopes finally peels back these layers, the revelations could dwarf even relativity or quantum mechanics in their impact. We might discover that dark matter is a swarm of primordial black holes, or that dark energy stems from extra dimensions curling in on themselves, or perhaps something entirely unforeseen, a truth so strange it reshapes reality as we know it. This isn't just astronomy, it's cosmic archaeology, digging through the universe's oldest light and structures to uncover laws that govern everything. And the tools we're building now are the shovels and brushes that will expose them. The hunt for dark matter and dark energy isn't about filling gaps in a textbook. It's about realizing we've been reading the wrong book altogether. And when the next chapter is written, it might just reveal that the universe is far stranger and far more wondrous than we ever dared to dream. For centuries, astronomical discoveries were locked behind the doors of elite institutions, researchers in white lab coats peering through data only a handful could access. But the future of space exploration is breaking those doors wide open, turning every smartphone and laptop into a potential window to the cosmos. Imagine a world where telescope data streams live to your device, where a high school student in Nairobi or a retired engineer in Buenos Aires could spot a supernova before professional astronomers. This isn't just a dream, it's the next frontier of citizen science, and it's rewriting who gets to participate in humanity's greatest discoveries. The shift is already underway. Projects like Zooniverse have shown the power of crowdsourcing, with volunteers classifying galaxies or tracking Martian weather patterns from their couches. But next-generation telescopes will take this collaboration into hyperdrive. Picture raw data from a lunar observatory flowing into an open-access portal, where AI pre-processes the flood of information before distributing chunks to volunteers worldwide. An amateur astrophotographer might notice an unusual dimming pattern around a star, potential evidence of a debris disk or even alien megastructures. A teacher running an after-school club could guide students in flagging atmospheric anomalies on exoplanets, contributing to real published research. The key, these telescopes won't just share polished findings, they'll broadcast the messy, unfiltered universe, inviting everyone to sift for gold in the cosmic data stream. What makes this revolution possible is a perfect storm of technology. Cloud computing lets servers handle petabytes of observations without burdening home devices. Machine learning acts as a first filter, highlighting intriguing anomalies for human review. and blockchain-based crediting systems could ensure contributors get recognized when their findings lead to breakthroughs. Imagine a future where scientific papers list thousands of co-authors, from PhDs to middle schoolers. Some prototypes even gamify the process, awarding points for classifying asteroid light curves or verifying exoplanet transits, turning astronomy into a global collaboration as engaging as it is profound. The implications stretch far beyond efficiency. By democratizing access, we're tapping into humanity's collective intelligence, the kind that once led a music teacher to discover a pulsar in radio telescope data, or a retired police officer to notice Jupiter's mysterious string of pearls storms. When anyone can explore the cosmos, we stop relying solely on professional astronomers and start benefiting from the pattern recognition of artists, the lateral thinking of gamers, even the tireless curiosity of kids. A distributed network of observers could catch transient events that slip past automated systems like the interstellar visitor Oumuamua, which was nearly missed until a postdoc combing through old data spotted its peculiar trajectory. But the most transformative aspect might be cultural. Open data telescopes could make space science a shared human endeavor, breaking down barriers between nations and disciplines. Picture classrooms in 50 countries collaborating to monitor a comet's breakup, or villages with limited internet access receiving curated data packets to analyze offline. The Vera Rubin Observatory's 10-year survey will produce over 500 petabytes, an avalanche no single team could process alone. By inviting the world to help, we're not just accelerating discovery, we're fostering a generation that sees the universe as theirs to explore, question, and protect. This isn't just about more eyes on the sky, it's about reimagining how knowledge is built. The great observatories of the future might not just beam data back to Earth, but spark a global conversation where every curious mind gets to whisper back. And in that exchange, we're not just mapping stars, we're rediscovering what happens when science belongs to everyone. Hubble's greatest advantage wasn't just its optics, it was its address. Orbiting just 540 kilometers above Earth, the telescope became the only space observatory in history to get a hands-on tune-up from astronauts. 5 separate shuttle missions repaired its faulty mirror, swapped aging instruments for cutting-edge replacements, and even gave it a literal boost to higher orbits. But what happens when the next great telescope isn't parked in our cosmic backyard, but stationed 1.5 million kilometers away at Lagrange Point 2 like James Webb, or even farther? At those distances, a repair mission would take years to plan, cost billions, and push human spaceflight to its absolute limits. The next generation of telescopes won't just need to be advanced, they'll need to be virtually self-sufficient, capable of diagnosing their own ailments and performing cosmic surgery on themselves. This reality is forcing engineers to rethink durability from the ground up. Consider micrometeoroids, tiny space rocks hurtling at speeds faster than bullets. While Hubble could be inspected and patched after impacts, distant telescopes have no such safety net. Solutions range from smart materials that bleed self-healing polymers into cracks, to mirror coatings studded with microscopic sensors that map damage down to the nanometer. Some prototypes even experiment with sacrificial outer layers, like a lizard shedding its tail, where outer panels absorb impacts before they reach critical components. But the real innovation lies in redundancy. Future telescopes might deploy with entire backup mirror segments tucked away, ready for robotic arms to swap in when primary ones degrade, like a spacecraft carrying its own organ donor. Then there's the challenge of moving parts. James Webb's Sunshield, with its 80 individual motors and 140 release mechanisms, was a single point of failure that kept engineers awake at night. Next-gen designs are minimizing mechanical complexity in favor of solid-state solutions. Mirrors that adjust their shape using magnetic fields instead of motors, or sun shields made of electrochromic materials that darken electronically without needing to unfold. The goal, a telescope with fewer moving parts than a smartphone, where even the moving components rely on quantum locking or electrostatic forces rather than gears and bearings. But the ultimate safety net might be robotic caretakers. Imagine a dedicated repair drone hitching a ride with the telescope at launch, then lying dormant until needed. When sensors detect a malfunction, this mechanical handyman could unfurl its tools, micro-welders to fix electrical shorts, grippers to clear debris from optics, even miniature 3D printers to fabricate replacement parts on demand. The European Space Agency is already testing such concepts with their Clean Space initiative, which envisions autonomous robots servicing satellites in geostationary orbit. Scale this up, and we could see fleets of maintenance bots stationed at strategic points across the solar system, ready to assist any telescope in distress. Yet the most radical approach might be accepting imperfection. Instead of striving for flawless optics that degrade over decades, future telescopes could employ adaptive AI that learns to compensate for damage in real time. A scratched mirror, the system recalibrates to prioritize undamaged segments. A jammed filter wheel, machine learning reconstructs missing data from other wavelengths. This philosophy shifts the definition of repair from physical restoration to computational resilience, a telescope that grows wiser about its limitations rather than fighting them. The stakes couldn't be higher. A single failed gyroscope or stuck shutter could turn a billion-dollar observatory into space junk if it's beyond our reach. But if these innovations succeed, they'll do more than save telescopes. They'll redefine how we build for the unforgiving environment of deep space, because the greatest discoveries often lie just beyond the edge of what we can fix, and the next generation of observatories will need to journey there alone. Building the next generation of space telescopes isn't just an engineering challenge, it's a financial odyssey that could redefine how humanity funds its cosmic ambitions. The James Webb Space Telescope's staggering $10 billion price tag sparked debates about sustainability, proving that traditional government-funded models may not scale for future projects. But here's the twist: the era of solo national missions is fading fast, replaced by a patchwork of creative funding strategies as innovative as the telescopes themselves. Take international collaboration, the financial equivalent of gravitational lensing, where shared resources magnify what any single country could achieve alone. The European Space Agency's Euclid mission, mapping dark matter with precision optics, splits costs across 21 nations. Japan's upcoming Speaker infrared telescope teams up with European partners to share both funding and expertise. Even NASA's next flagship, the Habitable Worlds Observatory, is being designed with modular instruments so international contributors can plug in their specialized hardware, turning a single mission into a global knowledge buffet. This isn't just cost sharing, it's risk sharing, ensuring that if one nation's budget stumbles, the project doesn't collapse, but government coffers alone won't cover the bills. Private capital is flooding into space astronomy like never before, with billionaires and venture funds betting on telescopes as both scientific tools and business ventures. Breakthrough Starshot, funded by tech mogul Yuri Milner, aims to laser-propel nanocraft to Alpha Centauri, but its lightweight optics research could revolutionize how we build affordable space telescopes. Companies like SpaceX slash launch costs, while startups explore asteroid mine materials to reduce mirror production expenses. The financial equation is shifting. where Hubble's maintenance required billion-dollar shuttle flights, future telescopes might hitch rides on reusable rockets for pocket change by comparison. Then there's the wild card crowdfunding. When the non-profit Planetary Society launched its light-sail solar sail demonstrator, 30,000 individual backers chipped in, proving public passion could translate to hardware. Imagine Kickstarter campaigns for telescope time, where amateur astronomers pool resources to buy observing hours on cutting-edge scopes, or schools crowdfunding to target specific exoplanets during science class. The upcoming Twinkle mission, a privately funded space telescope analyzing exoplanet atmospheres, already sells data access to universities at a fraction of traditional costs. This isn't just about money, it's about democratizing who gets to steer humanity's cosmic gaze. The most radical proposals rethink ownership entirely. What if telescopes operated like broadband satellites, with corporations building the hardware and selling data subscriptions to research institutions? Or blockchain-based models where telescope time is tokenized, letting scientists trade observation slots like digital assets. Some visionaries even pitch telescopes as philanthropic endowments. Imagine the Gates Array or Bezos' Deep Field Survey, where tech giants fund perpetual astronomy as their legacy. The financial innovations mirror the technological ones, lighter, modular, and adaptable. Just as next-gen telescopes shed bulky mirrors for flexible designs, their funding models are ditching monolithic budgets for agile, collaborative approaches. The result, a future where the price tag of discovery isn't a barrier, but an invitation for nations, corporations, and even classrooms to invest in humanity's next great eye on the cosmos. SpaceX's reusable Falcon 9 rockets have already slashed launch costs by a staggering 70% compared to traditional boosters, but the real revolution is just beginning. When NASA James Webb Space Telescope finally reached orbit atop an Ariane 5 rocket, the entire astronomy community held its breath, knowing a single failure would doom a $10 billion mission. Now, imagine a future where cutting-edge observatories hitch rides on SpaceX's Starship for a fraction of the price, with so much payload capacity that engineers can stop obsessing over every gram and focus on bold designs instead. This isn't science fiction, it's the new economics of space, and it's tearing down barriers that have constrained telescope missions for decades. Private companies are rewriting the rules with a startup mentality, moving fast, embracing risk, and iterating rapidly. While traditional space agencies might spend a decade perfecting a single mirror, SpaceX and Blue Origin are launching prototypes, learning from failures, and improving on the fly. Take the case of SpaceX's Starlink satellites. Though designed for internet service, their laser communication tech could revolutionize how space telescopes transmit data, enabling real-time streaming of high-resolution cosmic images without the usual bottleneck of radio bandwidth. And Blue Origin's New Glenn rocket, with its 7-meter fairing, could carry telescope mirrors so large they'd be impossible to launch on any existing vehicle, opening doors to designs that were previously just whiteboard fantasies. The ripple effects go beyond cost savings. Commercial players are democratizing access to space, offering rideshare programs where a telescope could piggyback on a satellite launch for less than the price of a luxury car. Startups like Rocket Lab are pioneering dedicated small satellite launches, perfect for deploying networks of mini telescopes that work in concert. Think of a constellation of shoebox-sized observatories monitoring the sky in shifts, providing 24/7 coverage no single instrument could achieve. Even the logistics are transforming. SpaceX's Starship promises in-orbit refueling, meaning telescopes could launch partially fueled to save weight, then top up their tanks in space before journeying to distant orbits like Lagrange Point 2. But the most disruptive shift might be in timelines. Traditional agency-led missions often take 20 years from concept to launch, longer than the careers of many scientists who proposed them. Private companies, driven by competition and profit motives, are compressing that cycle to under a decade. SpaceX's iterative approach, building, launching, and improving, could let astronomers test new telescope technologies in orbit within years instead of waiting for a once-in-a-generation flagship mission. Imagine a world where an engineering breakthrough in mirror coatings on Monday could be on its way to space by Friday, accelerating discovery at a pace academia alone could never match. Yet this gold rush comes with caveats. Corporate priorities don't always align with scientific ones. A company might prioritize profitable Earth observation satellites over pure research telescopes. And the breakneck speed of commercial space raises questions about long-term reliability. Will a telescope launched on a budget rocket still be operational in 10 years? The answer likely lies in hybrid models, where agencies like NASA fund the science while companies handle the logistics, blending the rigor of academia with the agility of Silicon Valley. The new space race isn't just about reaching orbit, it's about reimagining how we explore the cosmos. With private companies turning launch costs from a barrier into an afterthought, the next generation of telescopes won't be limited by budgets or bureaucracy, but only by the audacity of our questions. And when the first corporate-funded observatory spots an Earth-like exoplanet or catches a supernova in its infancy, it'll prove that the future of astronomy doesn't belong to any one nation or agency, but to anyone bold enough to shoot for the stars. The most profound legacy of the next great space telescope might not be the exoplanets it discovers or the cosmic mysteries it solves, but the millions of young minds it inspires to look up. Unlike the cloistered science of past generations, where telescope data trickled slowly through academic pipelines, the next era of astronomy will unfold in living color on smartphones and VR headsets worldwide. Picture a 12-year-old in Mumbai strapping on a virtual reality headset to stand on the surface of a newly discovered exoplanet, watching methane clouds swirl overhead in real time. Or a classroom in Brazil collaborating with students in Norway to track a supernova's brightness changes using raw data uploaded that morning from orbit. This isn't passive learning, it's participatory discovery where the boundary between scientist and enthusiast blurs into irrelevance. The tools enabling this revolution are already taking shape. Interactive data portals like the upcoming Legacy Survey of Space and Time will let users pan and zoom through petabytes of cosmic imagery like an astronomical Google Maps, flagging unusual objects for professional follow-up. Augmented reality apps could overlay telescope observations onto the night sky through phone cameras, transforming backyards into immersive planetariums where every star holds clickable secrets. And then there's the game changer, adaptive learning algorithms that tailor telescope data to users' interests. A budding biologist might receive alerts about exoplanets with potential biosignatures, while a physics student gets steered toward neutron star collisions ripe for testing relativity. The universe becomes a choose-your-own adventure book, with each reader following their curiosity. But the real magic happens when these tools converge with global observation campaigns. Imagine cosmic treasure hunt, weekends where millions worldwide sift through fresh telescope data to spot asteroids, variable stars, or gravitational lenses. The thrill of being first to notice something strange, a dimming star that could harbor megastructures, or a galaxy warped by dark matter, isn't reserved for PhDs anymore. Projects like Zooniverse have already proven the power of crowdsourcing, with amateurs discovering everything from pulsars to planetary nebulae. Now scale that up with real-time data from next-gen telescopes, and suddenly every smartphone becomes a portal to the frontier of human knowledge. The psychological impact of this accessibility can't be overstated. For centuries, astronomy has been a spectator sport for most, something done by others in distant observatories. But when a high schooler in Nairobi helps identify a comet, or a retiree in Tokyo notices an exoplanet transit missed by algorithms, they're not just learning about science, they're living it. These moments create emotional connections that textbooks never could. Studies show students who engage with authentic research, not canned experiments, are far more likely to pursue STEM careers. The next telescope could spark more future astronomers in a single data release than Carl Sagan inspired in a lifetime. Perhaps the most beautiful unintended consequence will be the cultural shift. When telescope data flows freely across borders and languages, it becomes a universal language of curiosity. A child in war-torn regions tracking the International Space Station's path via telescope feeds learns that humanity's greatest achievements transcend earthly conflicts. Indigenous communities might blend traditional sky lore with cutting-edge exoplanet discoveries, weaving new narratives that honor both ancient wisdom and modern science. This isn't just outreach, it's the democratization of wonder, proving that the urge to explore belongs to everyone with eyes to see and questions to ask. The next generation won't just watch discoveries unfold on news feeds, they'll make them from their bedrooms. And when one of those amateur observers eventually stands at a podium accepting a Nobel Prize for work that began with a telescope app on their phone, we'll realize the true measure of these instruments isn't in light years or megapixels, but in the countless sparks of curiosity they ignite across the globe. The breathtaking power of next-generation space telescopes comes with profound ethical dilemmas, questions that extend far beyond engineering into the heart of who gets to control humanity's cosmic perspective. Consider this: when a telescope can peer into the atmosphere of an exoplanet with enough clarity to detect city lights or industrial pollution, who decides whether to share that discovery with the world? Governments might classify such findings as national security risks, while corporations could hoard data for competitive advantage. Even scientific institutions face tough choices. Should they prioritize studying potentially habitable worlds, or avoid drawing attention to Earth's location in a galaxy that might harbor civilizations with unknown intentions? Data ownership sits at the center of these debates. Unlike Hubble's era, where observations flowed freely into public archives, future telescopes funded by private entities could operate under proprietary rules. Imagine a scenario where a company charges universities exorbitant fees to access critical exoplanet data, or a nation restricts telescope time to allies while excluding rivals. The very tools designed to unite humanity in exploration might instead become instruments of information inequality. Some astronomers propose a cosmic commons framework where all telescope data older than 6 months enters an open access pool, a compromise between commercial interests and scientific transparency. But with stakes this high, even voluntary agreements could fracture under political or economic pressure. Then there's the specter of militarization. The same adaptive optics that sharpen a telescope's view of distant galaxies could, in theory, be repurposed to track enemy satellites or missiles with terrifying precision. Materials engineered to withstand micrometeoroids might double as armor for orbital weapons platforms. History shows how quickly dual-use technologies blur the line between exploration and exploitation. GPS began as a military tool before revolutionizing civilian life. The difference now is scale. A space telescope's resolving power could make Earth's surface as legible as a street map, raising urgent questions about surveillance and privacy, even before considering extraterrestrial concerns. Speaking of extraterrestrials, what happens if a telescope detects unambiguous signs of intelligence beyond Earth? Current protocols, drafted in the 1990s, suggest international consultation before any public announcement. But these guidelines carry no legal weight, and in today's hyper-connected world, controlling such a revelation would be like trying to contain a supernova. A single tweet from a junior researcher could ignite global panic or euphoria overnight. Some ethicists argue for preemptive treaties establishing response protocols, while others warn against premature assumptions. After all, an alien megastructure might turn out to be a natural quirk of physics. The mere possibility forces us to confront uncomfortable truths. Humanity has never needed a unified voice before, but the moment we discover we're not alone, our divisions could become our downfall. Yet within these challenges lies an opportunity. The same telescopes that expose ethical fault lines could also help mend them. Collaborative projects like the Event Horizon Telescope, which networked observatories worldwide to capture the first black hole image, prove that shared scientific goals can transcend borders. Future missions might require similar cooperation, binding nations together through mutual curiosity. And by grappling openly with these dilemmas, now debating data access, demilitarizing observation tech, preparing for first contact, we're not just safeguarding astronomy's future. We're rehearsing how to be better stewards of our own planet, and perhaps one day better neighbors in a cosmos far wider than we've dared to imagine. Every time a rocket blasts off, it doesn't just carry a telescope skyward. It leaves behind a trail of environmental consequences. The soot from solid rocket boosters, the carbon dioxide from fuel combustion, even the aluminum oxide scattered in the upper atmosphere, it all adds up. A single heavy lift launch can release hundreds of tons of carbon emissions, equivalent to thousands of transatlantic flights. And that's before considering the growing swarm of orbital debris, where even a fleck of paint traveling at 17,000 miles per hour can cripple a satellite. The irony is stark. Instruments designed to study the cosmos are inadvertently polluting the very planet they're launched from. But the next wave of telescopes is tackling this paradox head-on. Engineers are rethinking propulsion, swapping traditional chemical rockets for cleaner alternatives. Imagine a telescope hitching a ride on a rocket powered by liquid hydrogen and oxygen, a combination that produces only water vapor as exhaust. Or better yet, one that reaches orbit aboard a vehicle using bio-derived fuels, like those being tested by companies like Blue Origin, which aim to cut emissions by over 90%. Some concepts go even further, employing electric propulsion systems that use solar power to ionize and expel inert gases like xenon, leaving no chemical traces at all. These systems may be slower, but they're transforming spaceflight from a smoky, high-impact endeavor into something far more sustainable. Then there's the issue of materials. Traditional telescopes rely on aluminum, titanium, and composite alloys, durable, but often energy-intensive to produce and nearly impossible to dispose of safely when the mission ends. Future designs are turning to biodegradable alternatives, like magnesium alloys that vaporize harmlessly upon re-entry, or mycelium-based composites that decompose naturally if they fall back to Earth. Even the gold coatings on mirror segments, a staple for reflecting infrared light, are being reimagined, with researchers experimenting with ultra-thin layers of recyclable materials that achieve the same performance without the environmental toll of mining and refining precious metals. Perhaps the most radical shift is in mission longevity and end-of-life planning. Instead of abandoning telescopes when they malfunction, engineers are designing them for repair, refurbishment, or responsible decommissioning. The European Space Agency's Clear Space mission, set to launch in 2026, will test robotic capture and removal of defunct satellites, potentially turning space junk into reusable scrap. Future telescopes might even come with built-in deorbit sails, lightweight membranes that unfurl to increase atmospheric drag, gently pulling the instrument back to burn up safely rather than lingering as debris for centuries. The stakes extend beyond Earth's atmosphere. As we push deeper into space, the risk of contaminating pristine environments like Mars or Europa with Earth microbes grows. Next-gen telescopes bound for these destinations will need sterilization protocols far stricter than today's, possibly using self-sterilizing coatings or ultraviolet light systems to ensure they don't accidentally export terrestrial life while searching for alien biology. It's a delicate balance. The same tools that could reveal life elsewhere must be scrupulously cleaned to avoid false positives or ecological damage. This isn't just about minimizing harm, it's about redefining exploration as an act of stewardship. The telescopes of tomorrow won't just gaze outward, they'll embody a philosophy that respects both the cosmos and the fragile world we launch from, because the ultimate goal isn't just to understand the universe, but to ensure we're still here, with a healthy, thriving planet beneath our feet when the next great discoveries roll in. The next great leap in space observation won't belong to any single nation. It'll be a symphony of global collaboration, with engineers from Tokyo to Toulouse and scientists from Cape Canaveral to Bangalore contributing their expertise. Take NASA's upcoming Habitable Worlds Observatory, a mission that's being designed from the ground up as an international project. The telescope's mirror segments might be polished in Germany, its spectrograph assembled in Japan, and its data processed by algorithms developed in India, all before launching on a European rocket. This isn't just about splitting costs, it's about pooling humanity's collective genius to build something no single country could achieve alone. When the European Space Agency's Euclid telescope began mapping dark matter, its success hinged on detectors built by NASA and calibration software from Canadian universities. These partnerships transform astronomy from a competition into a conversation, where breakthroughs have accents from every continent. The diplomatic ripple effects are just as profound as the scientific ones. Space agencies that might clash over terrestrial politics often find common ground in cosmic curiosity. During the tense geopolitical climate of the 2020s, the James Webb Space Telescope became a rare neutral zone, with NASA, ESA, and the Canadian Space Agency collaborating so seamlessly. The final product bore no flags, only mission patches. Shared telescope projects create quiet channels for cooperation, where engineers exchange ideas freely even when their governments disagree. There's a reason the International Space Station has outlasted every earthly alliance since its inception. When you're solving problems in microgravity, nationality matters less than ingenuity. Future telescopes could expand this model, perhaps even welcoming contributions from emerging space nations like the United Arab Emirates, whose Hope probe to Mars proved small programs can deliver giant insights. Financially, international collaboration acts as a force multiplier. Building a 30-meter mirror on Earth would bankrupt most individual nations, but spread across 20 countries, it becomes feasible. The 30-meter telescope project, though controversial, shows how shared funding unlocks otherwise impossible scales, with partners from China to Brazil contributing fractions of the budget in exchange for proportional observation time. This democratization of access means a graduate student in South Africa might study quasar data from a telescope her university could never afford to build, while a team in Chile analyzes exoplanet spectra collected by hardware they helped design. The result, a global generation of astronomers trained on cutting-edge tools, ensuring no single region monopolizes discovery. Yet the greatest value might lie in the diversity of thought these collaborations inspire. Different cultures approach problems in strikingly different ways. Where American engineers might prioritize computational power, Japanese teams often miniaturize components with breathtaking efficiency. When these perspectives collide around a shared blueprint, innovation flourishes. India's frugal engineering ethos, honed by budget constraints, led to their Mars orbiter mission costing less than a Hollywood space movie. Imagine applying that resourcefulness to next-gen telescope cooling systems or data compression. Similarly, African radio astronomers, working under pristine skies with limited infrastructure, have pioneered novel interference filtering techniques now used worldwide. The telescopes of tomorrow won't just reflect light, they'll refract the collective brilliance of humanity's many minds. This model does come with challenges, of course. Aligning time zones for virtual meetings can resemble orbital mechanics, and differing bureaucratic cultures sometimes slow decision-making. But the alternative, duplicative, siloed programs competing for the same discoveries wastes resources we can't afford in an era of climate crises and strained research budgets. Perhaps that's why the most ambitious proposal yet, the Lunar Crater Radio Telescope, is being designed as an open-source project from day one, with blueprints shared globally to invite unexpected improvements. In a divided world, these collaborative telescopes become more than scientific tools. They're proof that when humanity faces the cosmos, our best chance lies not in solitary genius, but in united curiosity. The stars have always belonged to everyone. Soon, the tools to study them will too. James Webb's agonizing 25-year journey from drawing board to orbit taught astronomers a brutal lesson. Perfection takes time, and taxpayers' patience has limits. But the next era of space telescopes won't play by those rules. While Webb was still unfolding its golden mirrors at Lagrange Point 2, engineers were already prototyping successors that could slash development timelines in half. The difference, a perfect storm of parallel breakthroughs from AI-accelerated mirror polishing to 3D printed components, combined with funding models that reward speed over exhaustive risk aversion. Take NASA Habitable Worlds Observatory, the agency's next flagship mission targeting the 2040 timeframe. Unlike Webb's sequential development where every subsystem waited its turn, HWO's teams are designing its coronagraph, mirrors, and spectrograph simultaneously, leveraging digital twins to simulate integration issues before hardware exists. Private sector tricks are bleeding in too. SpaceX-style iterative testing means launching smaller pathfinders like the upcoming Nancy Grace Roman Space Telescope to validate technologies at scale before committing to billion-dollar builds. The result, projects that once took decades might soon clock in under 10 years. But the real timeline disruptors are already in orbit. Miniaturized telescopes like NASA Acute CubeSat, no bigger than a cereal box, are proving that small, frequent launches can deliver big science at startup speed. Instead of waiting 20 years for a monolithic observatory, astronomers could deploy swarms of specialized micro-telescopes every few months, each targeting specific cosmic questions with laser focus. Private initiatives like the Breakthrough Watch program are pushing this further, adapting military-grade adaptive optics for exoplanet hunting in record time. Their secret, treating telescopes like software, upgradable, modular, and constantly evolving through patches rather than painstaking rebuilds. The wild card is international competition. China's Zhengzhou Space Telescope, slated for 2024, isn't just a Hubble clone. It boasts a field of view 300 times wider, promising to map 40% of the sky in a decade. This isn't merely science, it's a strategic sprint for cosmic real estate. where first movers claim prime observational targets. The European Space Agency's Pluto mission, launching 2026, will monitor 1 million stars for exoplanet transits, a dataset so vast it could ID habitable worlds before HWO even leaves the lab. Yet speed isn't everything. The most revolutionary telescopes might emerge from unexpected places. University labs 3D printing lightweight mirrors, or amateur astronomers crowdsourcing funds for niche instruments targeting stellar oddities. When the next paradigm-shifting observatory launches, it might not come stamped with a NASA logo, but from a garage in Berlin or a tech incubator in Singapore, proving that in the new space race, agility often beats bureaucracy. The future of cosmic discovery isn't on a 20-year roadmap, it's unfolding now, at the pace of a software update, rewriting what's possible one rapid iteration at a time. History loves its surprises, especially in astronomy. When Jocelyn Bell detected the first pulsar in 1967, she initially labeled the strange radio signal LGM1, short for Little Green Men, because the rhythmic pulses seemed too perfect to be natural. Fast forward to today, and pulsars are textbook examples of neutron stars, proof that some of the universe's greatest discoveries begin as head-scratching anomalies. The next generation of telescopes, with their unprecedented sensitivity and range, won't just confirm what we already suspect. They'll expose cosmic oddities we haven't even thought to question. Consider rogue planets, worlds untethered to any star, drifting through the void like cosmic nomads. Current estimates suggest there could be billions of these dark wanderers in our galaxy alone, invisible to traditional telescopes because they emit no light of their own. But a telescope equipped with hypersensitive infrared detectors and AI-powered motion tracking might catch their faint thermal glow as they pass through star fields. Even more intriguing, some of these rogue planets could harbor subsurface oceans kept liquid by geothermal heat, turning what we assumed were frozen wastelands into potential oases for life, no sunlight required. Then there's the enigma of cosmic strings, hypothetical cracks in space-time left over from the Big Bang, thinner than an atom but stretching across the universe. Predicted by string theory but never observed, these filaments would warp space around them, creating telltale distortions in the light of background galaxies. A telescope with nanometer-level resolution might spot these wrinkles in reality itself, offering the first tangible evidence for theories that currently live on chalkboards. It's like finding the seams in the fabric of the cosmos, threads that could unravel entirely new understandings of gravity, quantum physics, and the birth of everything. But the real surprises often come from the noise, the data astronomers typically discard as interference. When Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background in 1965, they first blamed pigeon droppings on their antenna. Future telescopes, sifting through petabytes of data with machine learning, could uncover similar mistakes that turn out to be revolutionary. Maybe it's a pattern of gamma-ray bursts too regular to be random, hinting at artificial origins. Or a star that dims in ways no known astrophysics can explain, suggesting megastructures built by advanced civilizations. The universe excels at hiding its wildest secrets in plain sight, waiting for an instrument sharp enough to notice. Perhaps the most humbling possibility, the next telescope could reveal phenomena that defy all existing models, something as baffling to modern science as quasars were in the 1960s. Imagine detecting a galaxy where the stars rotate in perfect geometric formations, or a region of space where time appears to flow backward. These aren't just plot twists for astronomers, they're invitations to rewrite physics itself. After all, every time humanity builds a better window to the cosmos, the universe responds by showing us how much we still don't know. And that's the true beauty of exploration. The best discoveries aren't the ones we plan for. They're the ones that leave us stunned, scrambling for new theories, and falling in love with the mysteries all over again. The hype around next-generation space telescopes is electric. Headlines promise alien biosignatures, dark matter revelations, and cosmic mysteries solved overnight. But here's the truth: science rarely delivers eureka moments on demand. For every Hubble Deep Field, that iconic image revealing thousands of galaxies in a speck of sky, there are years of meticulous calibration, frustrating glitches, and incremental discoveries that reshape our understanding pixel by pixel. The next great telescope won't beam back an encyclopedia of the universe on day one. Instead, it'll hand us a key to a door we didn't even know existed, behind which lie questions we're only beginning to articulate. Consider the hunt for extraterrestrial life. When James Webb detected carbon dioxide in an exoplanet's atmosphere, the internet erupted with whispers of alien proof. Yet seasoned astronomers tempered expectations. Those molecules could stem from volcanoes as easily as biology. The real breakthrough wasn't the detection itself, but the telescope's ability to tease apart atmospheric chemistry at interstellar distances. Each observation narrows the gap between speculation and knowledge, even when the headlines oversimplify. Future telescopes might spend a decade analyzing hundreds of exoplanets before stumbling upon a biosignature so unambiguous it silences doubt. The journey matters as much as the destination. Dark matter research follows a similar rhythm. For 50 years, scientists have chased this invisible substance through indirect clues: galaxies rotating too fast, light bent by unseen mass. The next telescopes won't necessarily capture dark matter like a photograph. More likely, they'll rule out wrong theories, tighten constraints, and perhaps isolate a handful of candidate particles from billions of possibilities. That's how science operates, not with Hollywood-style revelations, but through the slow, relentless elimination of uncertainty. When the Vera Rubin Observatory begins its 10-year sky survey, its greatest contribution might be a single anomalous data point buried in petabytes of imagery, a statistical hiccup that leads physicists down an entirely new path. What often gets lost in the hype is how these telescopes redefine the very questions we ask. Before Hubble, no one wondered about the acceleration of the universe's expansion. Dark energy wasn't even a concept. The telescope's observations forced that paradigm shift, rewriting cosmology overnight. Similarly, the next generation of instruments could expose flaws in our current models so profound that today's big questions seem quaint by comparison. Imagine a telescope detecting gravitational waves from cosmic strings, hypothetical defects in space-time, or spotting quantum fluctuations in the vacuum of space itself. These aren't just answers, they're invitations to deeper mysteries. So how do we balance excitement with patience? By celebrating the process, not just the prizes. Every blurry exoplanet spectrum sharpens our tools. Every null result in the dark matter hunt teaches us where not to look. And sometimes the most profound discoveries emerge from failed missions, like NASA's Kepler telescope, which persevered through broken reaction wheels to uncover thousands of planets, proving the galaxy teems with worlds. The next telescope won't hand us a completed cosmic jigsaw. It'll give us a few more pieces, along with the thrilling realization that the puzzle is far larger and more beautiful than we'd imagined. In the end, these instruments aren't just about collecting data, they're about expanding humanity's capacity for wonder. When Galileo first pointed his telescope at Jupiter's moons, he didn't just see celestial bodies, he saw proof that not everything revolved around Earth. The next great observatory might offer a similar humbling perspective, reminding us that the universe owes us neither quick answers nor easy truths, only the chance to keep looking, questioning, and marveling at how much remains to be seen. The most advanced telescope in the world is useless without the spark of human curiosity to point it in the right direction. Artificial intelligence can analyze data at lightning speed, robotic systems can perform flawless adjustments, but no algorithm has ever woken up in the middle of the night with a wild hunch about where to search for alien megastructures. That flash of insight, the moment when a scientist looks at familiar data and sees something everyone else missed, is where the real breakthroughs begin. Think of Vera Rubin staring at galaxy rotation curves in the 1970s, noticing stars moving too fast at the edges, and daring to suggest the unthinkable, that the universe was filled with invisible matter. No computer would have made that leap. It took a human mind willing to challenge orthodoxy. This partnership between human intuition and technological precision defines the next era of discovery. When the James Webb Space Telescope detected potential signs of life-friendly molecules on exoplanet K218b, it wasn't an autonomous system that flagged the anomaly. It was a team of researchers who recognized the bizarre combination of methane, carbon dioxide, and dimethyl sulfide as eerily reminiscent of Earth's own chemical fingerprints. Machines excel at processing, humans excel at wondering what if. Together, they form an unstoppable team. Future telescopes will amplify this dynamic, giving scientists unprecedented freedom to test theories that would have been dismissed as fantasy a generation ago. Want to scan 1,000 galaxies for evidence of Type 3 civilizations? Customize your observational parameters and let the AI handle the tedious work while you focus on interpreting the outliers. The beauty of these tools lies in how they democratize genius. A graduate student in Kenya with a bold hypothesis about dark matter distribution can now access the same observational power as a tenured professor at Harvard, thanks to open data policies and shared telescope time. When the next Vera Rubin or Carl Sagan emerges perhaps from a village with no astronomy department or a country with no space program, they won't need to wait decades for access to cutting-edge instruments. The barriers between curiosity and discovery are crumbling, and that's how revolutions begin. Yet for all their sophistication, telescopes remain conduits for our most human traits: wonder, stubbornness, and the relentless urge to peek over the next cosmic horizon. When the Event Horizon Telescope captured the first image of a black hole's shadow, it wasn't just a technological triumph. It was the culmination of a 100-year conversation started by a patent clerk named Einstein scribbling equations about warped spacetime. Every spiral galaxy mapped, every exoplanet atmosphere analyzed, carries echoes of those who came before. The naked eye astronomers of ancient Babylon, Galileo grinding his own lenses, Henrietta Leavitt discovering the yardstick of the universe in flickering variable stars. The next great telescope won't just expand what we see, it will expand what we dare to imagine. Behind every pixel of data, there's a researcher staying up late to chase a hunch, a student questioning textbook assumptions, or an amateur stargazer noticing a pattern professionals overlook. Machines measure, humans dream, and in that alchemy lies the secret to unlocking the cosmos. The data firehose from next-generation telescopes won't just challenge our technology, it'll redefine how we think about cosmic discovery. Imagine the Vera Rubin Observatory's legacy survey of space and time scanning the entire southern sky every few nights, generating more raw images in a week than the Hubble Space Telescope did in 30 years. That's not a trickle of information, it's a tsunami, with a single night's observations enough to fill 20,000 high-end laptops. Traditional astronomy workflows, where researchers download datasets to analyze on local machines, will crumble under this deluge. The solution, a radical shift toward edge computing, where preliminary analysis happens onboard the telescope itself. Instead of beaming down every pixel, these smart observatories will process images in orbit, flagging only the most intriguing anomalies for transmission. It's like having a team of virtual astronomers in space, sifting through cosmic static to pinpoint the needles in the haystack before the haystack ever reaches Earth. But raw processing power is only half the battle. The real game changer lies in how we extract meaning from this data storm. Machine learning algorithms, trained on decades of astronomical observations, will act as cosmic curators, identifying subtle patterns no human eye could catch. Take transient events like supernova. Current surveys might spot a few hundred per year. With next-gen telescopes, that number could explode to millions, requiring AI to triage which explosions merit follow-up based on rarity, location, or unusual characteristics. Some systems are already demonstrating this capability, like the Zwicky Transient Facility's automated alerts that guide astronomers to potential kilonovae collisions of neutron stars that forge gold and platinum in their violent wakes. The most revolutionary processing might happen beyond classical computing entirely. Quantum algorithms, still in their infancy, show tantalizing promise for solving specific astronomical problems exponentially faster. Simulating molecular interactions in exoplanet atmospheres, a task that bogs down supercomputers, could become trivial with quantum systems modeling quantum phenomena. Google's Quantum AI Lab has already demonstrated how quantum machine learning can classify galaxy morphologies using a fraction of the data classical models require. While universal quantum computers remain years away, hybrid systems combining classical and quantum processing could soon handle niche tasks like untangling the spectral fingerprints of complex organic molecules in distant nebulae. Yet the biggest hurdle isn't computation, it's human collaboration. When datasets grow so vast that no single institution can host them, astronomy becomes a cloud-based science. Projects like the NOIR Lab's Astro Data Lab are pioneering virtual environments where researchers worldwide can analyze shared datasets without downloading terabytes. Imagine a graduate student in Mumbai running complex simulations on Rubin data stored in Arizona, while an amateur astronomer in Norway cross-references those results with X-ray observations from a European Space Agency server. This federated model turns the internet into one giant distributed telescope where discoveries emerge from the interplay of global perspectives. The data revolution demands new skills from astronomers too. Future researchers might spend less time peering through eyepieces and more time crafting neural network architectures or debugging pipeline code. Already, observatories like the Square Kilometre Array are recruiting as many data engineers as astrophysicists, preparing for the day when their telescope generates more data traffic than the entire global internet. The job description of an astronomer is evolving from cosmic cartographer to information alchemist, transforming raw data into knowledge through an ever-shifting toolkit of computational wizardry. What makes this transition so thrilling is its democratizing potential. Cloud-based analysis means a high school student with a laptop could theoretically discover a new class of variable stars, while citizen scientists might train custom AI models to hunt for interstellar comets. The barriers to cosmic exploration aren't just falling, they're being obliterated by the very data flood that once seemed overwhelming. And when the next great discovery emerges from this chaos, it won't just tell us something new about the universe, it'll reveal how adaptable human curiosity can be when faced with the infinite. The telescopes of tomorrow won't just change how we see the universe, they'll transform how we see ourselves within it. Picture this: a decade from now, an orbiting observatory with a mirror assembled by robots unfolds like a mechanical lotus, It's adaptive optics guided by artificial intelligence that learns from every photon it captures. Meanwhile, a swarm of shoebox-sized satellites dances in formation, combining their gaze to spot an Earth-like world 100 light-years away. These aren't distant fantasies, they're blueprints in labs today, where engineers and scientists are quietly dismantling every assumption about what a telescope should be. What makes this moment so extraordinary isn't just the technology, it's the questions these instruments will let us ask for the first time. When Hubble launched, we didn't know exoplanets existed. When Webb deployed, dark energy was still a controversial hypothesis. The next great telescope will inevitably reveal phenomena we can't currently imagine, rewriting textbooks before the ink dries on their first editions. Maybe it'll catch the flicker of a Dyson sphere under construction around a distant star, or perhaps it'll trace the gravitational ripples from colliding universes in some higher dimension. The only guarantee is surprise, because every time humanity builds a better window to the cosmos, the universe shows us how much we've been missing. Yet beyond the scientific breakthroughs lies a deeper revolution. These telescopes are becoming extensions of human curiosity itself. An amateur astronomer in Nairobi might train an AI model that helps identify a new class of pulsars. A high school student in Buenos Aires could analyze telescope data during lunch break, spotting a comet that professionals overlook. The barriers between discovery and everyday life are crumbling, turning cosmic exploration into a shared human endeavor rather than an exclusive academic pursuit. Standing at this crossroads, we're not just building better tools, we're rediscovering what it means to wonder. Those golden mirrors and quantum sensors orbiting overhead aren't merely collecting data, they're reflecting our timeless urge to reach beyond what we know. And when the first images from these next-generation observatories finally beam back, they won't just show us new stars or galaxies. They'll reveal how far human ingenuity can stretch when we dare to reimagine the possible. So whether you're a scientist, a stargazer, or someone who occasionally glances up at the night sky and feels that ancient spark of curiosity, remember, the greatest cosmic revelations aren't behind us. They're waiting in the light of stars we haven't focused on yet, hidden in wavelengths we've just begun to decode, whispering to the next generation of dreamers who'll point these incredible machines toward the unknown. The universe has been keeping secrets for billions of years. Soon, we'll have the tools to finally hear its